Okay, so Tina's going to talk to us on quantum mixing through the algorithmic lens. Go ahead.
Okay, thanks, Ada. Thanks also to the organizers for organizing this nice workshop and for the invitation. Given this is the last talk of the day and everybody's probably in need of coffee and lots of other beverages, so I decided, thank you also to the organizers for indulging me to give a board talk. So it'll be hopefully an easygoing, informal board talk about some topics that sort of biased, subject to my personal bias. But I'm hoping to show you maybe sort of problem mixing in quantum walk and with a sort of an algorithmic sort of point of view. Yeah. And please stop me at any point in time. I might stumble here and there, and I'll ask the audience to help me with some of the questions. Yeah, so I might slip here and there, but do help me. Okay, so we have a graph X, and let's say we pick a matrix associated with X, and so let's say I'll pick the Laplacian, but this could be any other Hermitian matrix, adjacency matrix, or any other matrix. Okay? Associated to the graph. And so I would like to contrast these two models, random walk and quantum walk. So we are, another caveat is we're going to focus only on continuous time. And sort of a continuous time random walk model, you would take something like this. Right. And then analyze how this matrix transform probability distributions, essentially. Okay. So let's do a running example. Our favorite example is of course K2. Okay, so can somebody help me with the Laplacian of K2? I'm checking that the Laplacian is okay, actually. So what is the Laplacian of K2? Somebody help me.
It's 1 minus 1 minus 1, 1.
Thanks, Crystal. Yeah.
Yeah.
Right. So that's identity minus the poly X. Right. Good. Can somebody help me with the spectral decomposition of this guy?
0.
0 is the eigenvalue. What is the eigenprojector?
Half J.
Half J. Thank you. What's the other eigenvalue?
It's 1 or 2.
2. Thank you. Yes.
2.
And the other eigenprojector, of course, there's only 2 dimensions here, so it's this guy, because they have to sum up to I, right? That's okay, right? Yeah. Good. So then we can analyze this one. Then just by hitting this by a spectral theorem, what do I get? Exponential to 0, it's just 1. Eigenprojector stays, and then exponential applied to this one, and then the eigenprojector stays. Right? That's okay. Actually, I need more space here. Okay, good. So as we take t to infinity, what should I get here?
Half J.
Half J. And this matrix is, of course, a flat matrix. So we have uniform mixing, right? That's okay, right? Everybody happy? Okay. Okay, let's go to quantum. And there's nothing surprising here. In the quantum, of course, we're going to introduce the I. Still using the Laplacian, right? And we're going to do the same business, essentially. Right? Okay, somebody help me here. So what are we going to get here? So I'm going to use this function now instead of e to the minus t, e to the minus it now. So what do I get here? Still the same, right? Because the eigenvalue is 0. So yeah. What should I get here? Checking my notes also, just in case.
You just put an I in.
Yep, exactly.
Exponent.
I, and then this guy. Now we squint a little bit. So this is going to be, so please check this. Yeah, so I think up to some global phase, this is the thing we know. Yeah, that's okay, right? Up to a phase, I think. So you have to allow, maybe there's some mischievous phase here that's like this maybe, but I might be off, but please check. But a phase, we don't care about the phases because when we measure it disappears. Okay, so we get excited here because we say, okay, at time t equals pi over 4, what do we get here? We get a flat matrix. Right. And if we apply the measurement, then let's say we start the quantum walk at this vertex, then we subject this to measurement, then we get 1/2, 1/2. Because we take the absolute value squared of those guys. Okay. So the probability is, if you were to measure this at pi over 4. Okay. So let's contrast these two cases. What's interesting here is, so we can sort of say, in the classical case, we have to converge, right? So this we get uniform mixing, but it's convergence. So it's only in the limit. But in a quantum case, this is exact. We actually hit this 1/2, 1/2 exactly, right? So there's no convergence here. And moreover, in the classical case, this is infinite time. In the quantum case, it's finite time. Okay. So that's interesting observation in some sense. Okay. So let me put here. So this is Fari and Goodman, I guess, was credited to be the first who look at continuous time quantum walk. Okay, good. So right, so I'm supposed to sprinkle questions here. Okay, so the first observation is, if X is a regular graph, then it doesn't matter whether we use the Laplacian or the adjacency matrix. This is okay, right? Because the diagonal degree matrix is just identity up to some, to the degree. Okay, so I guess what I'd like to ask, so question. I think I know some of you know the answer of this. But okay, so do you know of an example of a graph, like a non-regular graph with Laplacian uniform mixing? So this example we had seen, it's K2, which is regular. So that's not interesting. So what about non-regular? Actually, we want a family. So we want a family. But I do know one example. So infinite family. So as a hint, can somebody give me a graph on 4 vertices, that non-regular, that they think might have this property?
The claw, K13.
That's adjacency.
So what's the Laplacian on this? This is not the example I was thinking, but Crystal might be right. Okay, I'll just tell you the example I know, and then okay. So the example I know is K4 minus an edge. But I don't have a family on this. This is the only one. But you can check this. This one. Yeah. So yeah, we'll come back to this. But adjacency, I know this is true. and this is due to harmony, right? Right. But I think this is adjacency. And because this is irregular, non-regular graph, the adjacency and Laplacian are different. So, okay, let me make this as a.
Sorry, Tino, but if you have a graph and its complement, don't they have to have uniform mixing at the same time?
So you're asking if complementation preserves Laplacian uniform mixing?
Because yeah, because they have the same eigenspaces. They have the same idempotent things. Because it's just like, right?
I think there's
Do
a
they not?
restriction on the size because there's a J matrix. That is. That may be causing-
So based on Crystal's comment, I'd like to put another question here. This is good. I like to have graph operators. Do we know of graph operators? Unary or binary, but unary is also okay. That preserve uniform mixing. Let's say unary. So Crystal's suggesting complementation, I think. But yeah, this will be interesting. So for binary, I think we know the Cartesian product, right? Self Cartesian product in some sense. So if graph has a uniform mixing, and you just take the powers using Cartesian product, it preserves uniform mixing. But do we know other operators maybe that can preserve uniform mixing? So Crystal, let me come back maybe. So we will come back to this graph later. Is that okay? Okay, there was also K13. That's a guess. Okay, good. Okay, so let me move ahead here. Okay, so right, so let's do a recap. So I would like to mention this another viewpoint. This is work by Aharonov and Tashma. This is on state generation. So let me drop back to K2. So we have look at K2, and then what we observe above was that we could bring 1, 0, essentially using that unitary transformation. We could bring it to this state, right? This state. So in the parlance of quantum computing, this is cat 0 going to cat 0 minus I cat 1. Okay, in some sense. Is that okay? So this is our when X is this. Okay, so suppose we are not happy. We said no, I don't want this state, but I want the other one that is a little bit more standard, and that is this guy. I'd like to bring it to this one. I'd like the target to be this one. Not this one, because I'd like to generate the state that is this state, and which people normally call the plus state. Okay. So can somebody tell me if this is possible or not? Can we instead generate the 1, 1 state as opposed to the 1 minus 1, 1 minus I state? Is this possible at all? Or can we rule this out immediately? Any comments? Is this impossible or this is possible?
It's impossible.
It's impossible?
Mhm.
Why?
Because it's in an eigenspace,
Yes.
and you can't go
Yeah.
backwards to the original
Right.
state. Yeah.
This is impossible because if we could go from 1, 0 to this state, then we could go back, right? So we could go from 1, 0 to this state, 1, 1. Then we could go back because we're doing unitary transformation. It's invertible, right? But the going back is nonsense because this is an eigenvector. If you start in an eigenvector, you can never leave that eigenvector. So this is not possible. Okay, so no. Okay, so next question: can we tickle K2 so that this is possible? Can we do something to the K2 so that the answer here is yes, I can do that? Can somebody suggest a modification to this graph so that we can really generate the plus state?
But wait, I and minus I?
Yes, yes, very good, very good. Right. So if we generate this, that's right, this. So now let's look at this oriented K2, right? And what is the matrix here? What is the matrix of this guy? This matrix should be familiar to everybody, no? Okay, so I'm abandoning Laplacian now. I'm just going to adjacency now. But I think okay, so that's another complication. Okay, so I'm gonna run to the adjacency now. But what is the name of this matrix? It's the poly Y. It's the
Z?
poly Y. Nope, it's a
Y?
poly Y. Yeah, poly Y. Right. So now I claim if you use this to do this, then it is now possible. I'll leave this as an exercise. Now you can really go. Okay, you can just check the eigenvectors of this is no longer 1, 1. Of course, that's the way we get this. It's just 1 plus minus I think. Okay, so it's possible to generate this thing. Okay, good. So good. So Aharonov. So let me mention this in the context of this paper by Aharonov and Tashma. They actually the question they ask is the following. So is it possible? So given a distribution, probability distribution, say P, over the vertices of the graph, can we generate the state that looks like this? This state. So this is a state that sort of mimics the distribution over the, P over the vertices of the graph. So this question we just asked is the case where we have a uniform distribution, classical uniform distribution on the vertices of the graph.
They require all the probability amplitudes to be real?
Yeah, so this is just a standard distribution. So yeah, so this is just this is 0, 1 over the space, and they sum up to 1. Yeah. So between 0 and 1. Is this okay? So this is like asking to get 1 over root 2, 1 over root 2, right? Because 1/2 is the distribution over K2. Okay. So of course, K2 alone can generate any distribution. simply because we are running on K2, going back to the Laplacian, we are actually running over this function, right? So it's actually when you measure this, you're actually getting cosine square sine square t. And of course, you can generate any 2-point distribution on this. So on K2, it's fine. But they ask this question more generally, I think. Okay, so let's, everybody okay? Okay, so let me, okay, so now what we're gonna do is we're going to generalize K2 in several directions. And based on time, we'll see how this goes. So I'd like to generalize K2 in at least 3 ways. And then we'll see whether we have time to do all 3. Okay, so the first one. So let me guess if you can. So maybe I'll ask the audience. Where do you want to go? How should we generalize K2? What's your favorite generalization of K2 as an infinite family? I'm hoping for an answer. Okay, very good. Yes, thank you, Sophia. Complete graph. I'm thinking of another thing actually, but complete graph we will do. Sorry? Hypercubes, yes, thank you. Somebody said hypercubes, yes. That's the thing I was, okay, hypercubes. And I think Harmony says path, okay. Yes, okay.
Cycles.
Cycles, yes. I was hoping Natalie would still give a talk actually, then the cycle would be covered there, but yeah, cycles is also possible. Okay, but let's go here first, because this is more like in line with the where the results started, sort of. Yeah, okay. But yeah, so we'll go here first. We'll go here next, and then not quite path, but another one actually. So can somebody suggest another one that is sort of a generalization of this? Something that Crystal mentioned earlier.
Graphs with 2 vertices.
No, I want families. I want infinite families.
Stars?
Yes, thank you. Stars. Very good. So I'd like to cover these guys, these classes, okay? And let's reserve these for maybe later or something. Okay, good. Okay, let's go to the hypercube. So why? Because this is a classic result of Moore and Russell. This is how this sort of mixing speed up started. Okay, so so the thing with the hypercube is it has this nice recursive structure, right? So it has this. So how do you build the n-dimensional n cube? So you pick n-1 cubes, 2 copies of those, and then you just add parallel edges. So because of this, the adjacency matrix is very nice. So it has this block structure. And then it's not too far away from here. You can use induction to prove that you can write this adjacency matrix of n cube as a sum of commuting terms, where each term is a tensor product of n things, which are just 2 by 2 matrices, where you're just sliding the poly x across this tensor, C of tensor i's. Right, so all the way to the last one. I think this is well known. Okay, so you can write this adjacency matrix as this sum, and the observation here is this is a commuting sum, okay. And because of this, you can analyze the quantum walk on the hypercube. So now I'm doing the adjacency, but it doesn't matter because this is a regular graph. So the Laplacian will also be the same, essentially. Yeah? So because of this decomposition, you can write this in terms of K2, which is Q1, right? So it's just Q1 here. Tensor product with itself, n times. Yeah. So the nice thing here is, okay, so we know this has uniform mixing at time pi over 4, right? So it's going to give us something looking like this. And of course, in the n cube, then what you do is you just tensor this with itself. And that's a flat state. Right. So the amplitudes are all the same. So uniform mixing again at time pi over 4. Okay. So let me ask this: what if I don't want this state with local phases? The answer is already, we already did the answer. What if I want this uniform superposition here? So I want the uniform superposition over all 2 to the n states, no local phases. So I don't want this one, but I want this one. What should I do? And you can see that if you've seen sort of quantum algorithms, this is usually the starting point in many quantum algorithms, because what you do is you have a bunch of ket zeros, and then you pipe them into Hadamard gates, right? So this is usually the starting point of many quantum algorithms. And the state that's being generated here is exactly this state. So in the spirit of Aharonov Tashma, suppose we want to generate this state instead of this state that has local phases. So what can I do? How do we hijack the hypercube?
Use a
Somebody's-
Hadamard matrix instead.
Sorry, Bill?
Use a Hadamard matrix instead. Or,
No. So
the
in terms
tensor
of this commuting terms,
or the tensor product of the replace sigma x with
Yes,
this sigma
exactly.
y.
Exactly. Yes. Good. That's okay, right? I think hopefully that's obvious. So then you get an oriented hypercube essentially. This is going to give you an oriented hypercube. Oops. That's going to generate this state here for us. Okay, so let me show you what Moore and Russell argued about in their paper. They want to argue there is a mixing speedup on the hypercube. So what is the argument? So they say, okay, so if you do a random walk on the hypercube, what would you use? You would use a stochastic matrix that look like this. So you take the adjacency. Now you have to be careful. This is not a stochastic matrix, right? So a classical random walk. So I'm also now sort of cheating because I'm switching to discrete time actually. But okay, indulge me a little bit. So this is the stochastic sort of matrix. Why? Because the n-dimensional hypercube has degree n, right? So you have to divide by, to make it stochastic, you have to divide by the degree. But now this is a problem because this is a bipartite graph, so it's not going to converge to anywhere because it's just going to flip flop. So what we can do is so this is stochastic, but it's not good because it's bipartite walk. So what we do is we just do a lazy walk. So we do like this. So take a lazy walk where you introduce this stay with probability 1 and with 1/2, and probably 1/2 you do the bipartite walk. So if you do this, then there is a classic result apparently that you converge to uniform mixing, to uniform distribution in time n log n. But you can see in the quantum walk when we use this. So I'm just going to ignore this this scaling factor, just absorb in the time, and I can ignore the identity because this is just going to introduce global phase. Right? So then the quantum walk is just going to do something like this. So we know what's happening here with this quantum walk. It's going to uniform mix at time pi over 4, right? But to compare things that are fair. I have to scale this matrix also. So when we scale this by n, I have to put an n here. So then the time here then t times n is going to be n pi over 4. Right? Because without the scaling, we know at pi over 4 it's going to uniform mix. But with this comparison with the stochastic matrix here, then the time is this, and this is order n, as opposed to the lower bound that's n log n. So this is a speed up. So you lose this log n factor. So this brings me to the question. Can we have a faster speed up? Is it possible? Can we find a graph where the speed up is bigger than this? If we are greedy, maybe just ask exponential speed up. But I'm not even sure this is possible. Can we have exponential speed up? Or can we prove that it's not possible? I don't know. Okay, good. Any questions so far? Are we okay? Okay, good. Right. Okay, so right. So I promise I will go to the clique next, right? Yeah, okay. Let's go to the clique. Okay. All right. So cliques. Okay, so right. For the cliques, what do we have here? So let's say this is a clique of size n. So I can draw this by isolating a special vertex here. Let's call it A. And this is everybody else. And of course, this is a clique of size n minus 1. This is everybody but A. Okay. All right. So and this this piece is n over n minus 2 regular. So so what happens if we do a quantum walk? So it doesn't matter, this is regular, so I can use adjacency or Laplacian. Can somebody tell me what happens if I do a quantum walk on starting here? I guess starting here. Actually, it doesn't matter starting anywhere because it's a vertex transitive graph. Okay, so can somebody tell me what is the profile of this matrix? Is it okay if I say this is approximately identity? This is a result by Chris. And he called this sedentary graphs. What this means is you are never going to escape this vertex, hardly, for any time. But I'm being loose here because this is subject to asymptotics. But it's pretty much, we are stuck at the starting point. Yeah. Right, so my question here is, a question I'd like to ask. So the cliques are famous expanders, sort of the best expanders, right? So I'd like to ask if are all expanders sedentary? Essentially asking what is the cause of this us being stuck here. Okay, so but if you look at this picture, there is a nice equitable partition. I mean, it's staring at us in the face here. Right? So so there is a two cell equitable partition. Yeah. So can somebody tell me what is the quotient graph of this clique here under this two cell partition? So there is an equitable partition that is just A alone in one cell and everybody else together in the other cell. Right, two cell. And I like to form the quotient.
You want the symmetric thing, Tino, or
Yes,
you want
I'd like
the
to. Yeah,
normal
the symmetric.
thing for us?
The symmetric.
Okay. So the vertex has 1, and the thing has like root n-1. The
Thank
edge
you.
has, yeah.
And then, there is a
n-1.
self loop here.
Yeah.
Yeah, thank you. Thanks, Christino. Okay, so we are starting here. And from Chris's observation here, we are never going to get out from A. In the quotient or not, doesn't matter. You're going to get stuck, right? So what is the most sensible way to escape A? How do we escape A? If we can tickle this graph, how do we escape A? What is the best way to escape A if we can change this quotient graph?
You just delete the loop.
Okay, yes. I want to do the other way around, the opposite of deleting the loop.
Okay, so do you want to add another loop?
Yes, thank you. Yes, thank you. Yeah, let's add another loop. Okay, so that corresponds to adding a loop here. Okay, so now my question is, what happens if we do a quantum walk on this graph now? Let's do a quantum walk on this graph. This is going to be equivalent to a quantum walk on what graph?
On the graph without the loops?
Yes, even more.
Is it K2?
Yeah, it's going to be equivalent to a quantum walk on just K2. Because, okay, so the argument, so this is a little bit loose, yeah. The weighting, the square root n-1 weighting, we can just move to the time, right? We can factor that into the time. And the self loop is just like identity shift, which doesn't matter in a quantum walk. Okay, so what this means is we can escape A. Not only that, we can actually land on the opposite side of A at time power 2. So there is perfect state transfer on this one. At time t equals pi over 2, which means we can actually arrive here, right? If you allow time scaling of this, of course, this is the time you have to use essentially, because this factor square root of n-1 is absorbed in the time. The diagonal n-2, the self loops doesn't matter because it's just a global shift. And then it's just a phase factor, right? Okay, so let's go back to let's lift this. So let's go the opposite. Let's do a lift instead of a quotient, right? So if we are here, that means we are actually here. Right? So you can argue if you lift it back, then this after PST time, what you get is something like this. You are not at A, but you are equally likely in all the vertices not in A. That's not A. So you have something like this. So if you look at a picture back in the lifted picture, you're here, and then now you have to allow me some asymptotics. So I'm going to assume this is close enough to asymptotically with n. This is close enough to this one. Because they only differ essentially in this coordinate. Okay. So modulo those approximations, essentially what this is saying is if you allow for this, so you have this click, right? So you have a click, and then we allow this self loop to be added, as Sophie had suggested here. Then this evolution actually can bring us from this to this, up to some asymptotic factor, right? Is that okay, more or less? So now we look at this the opposite way, because it's a unitary evolution, so we can go back and forth. So if we view this backwards, this is what you would call Grover search. Actually, it's called spatial search because it's continuous time, but it's the same. Because Grover search starts with an equal superposition, uniform superposition, and it hits a particular target, which is a marked vertex. And it's marked by this self loop, and you can view this as an oracle, actually. Okay. That's sort of the oracle that's influencing this. So this is like a rank 1 perturbation of the adjacency matrix of the clique. So this is all observed by Fari and Goodman. Okay, right, good. Any questions? So here, what we've seen is Grover search is actually a form of reverse mixing. So going this way is uniform mixing. But going the opposite is Grover search, essentially. Is that okay? Questions? Okay, good. All right, good. So on to the third one. So I should label these. Right, so this is the second one. So let's go to clause. Actually, I'm giving away the game here, but so right, okay, that's okay. I'd like to define a game. A game between two players. So let's say Alice and Bob, standard choice. And what they have as an input is a graph X. Graph X. And the game proceeds as follows. Alice goes first. Alice will choose a distribution. This is like the Aharonov-Tashma sort of thing. Distribution over the vertices of the graph X. Okay. And Bob goes next. Bob chooses a weighting, edge weighting. So this is W, weighting on the edges of the graph. Okay. Okay, so now the rule of the game is the rule of the game is Bob wins. Let me just stick a one. Bob wins if and only if there exists a time for which when the quantum walk is run. Okay, so I'm switching to adjacency now. On the graph X weighted with this edge weighting, like that. Okay, so this is subject to discussion actually here. So this amplitude has to be this for all B. So what is this game on this graph X? So Alice challenged Bob with a distribution of the vertices. Bob can weight the edges of the graph, and he'll win if the quantum walk on the edge-weighted graph, according to his chosen weights, starting somewhere, will generate essentially, so this is a state generation again, will generate this distribution that Alice had picked. Is this game clear? Any questions?
So what is the EA?
Yeah.
Okay, yes. So do we want to be cruel to Bob or not cruel to Bob? So if we don't want to be cruel to Bob, then Bob can pick A. So there exists A. If we want to be cruel to Bob, then we say for all A. Okay, so maybe it'll be nice to Bob, maybe. Okay, so I gave away the game here. So if somebody asks you, here's a graph X, and here's the game, would you play this game as Bob or not? Right. So we know that on K2, if we are Bob, we say yes, we'll play Bob. We don't have to weight the graph at all because any distribution you can generate on K2, we can cover it with the cosine square and sine square, right? Due to harmony's result, well, okay, so this is a special case. So on K13, right, if we play the game on K13, and Alice happened to choose a uniform distribution, then Bob wins under even this condition. Under any starting point, we can generate a uniform distribution. Okay. Okay. So I'd like to show you. So the thing I want to mention actually is this claim, which I did a while back. Bob wins on the claw. With the remaining, okay, so let me state the open question first, and then if we have time, I'll quickly sketch what's going on with this graph. Yeah. Ada, I'm running out of time, right? I'm out.
Oh, you have a few more minutes, yeah.
Okay, so maybe I cannot give you the proof, but okay, so but the proof is not too bad. Okay, so my question actually, the running question is, what other graphs? Where Bob can win. Oh, Bob can win. So to disallow cheating, maybe we should say the weights cannot be 0, because otherwise Bob can start deleting edges. So that's a little bit, yeah. And it's clear the graph has to be connected in some sense. And I think we can assume also the distribution has to be full support. Okay. So yeah, I don't think I have time to sketch this, but it's a 2x2 linear algebra problem actually. So it's not too bad. But I'd like to mention as a follow-up here, and this is probably the last thing I will say. So for the longest time, I was thinking, so can I ask, what would your candidate for the hardest possible graph where you think Bob cannot win? If you had to guess an X for which Bob is probably going to lose. So on the claw, he can win. In a sense, because the claw behaves like K2 in some sense. It's like K2 in hiding, actually. Okay, so let me just say this.
So if you take a Cartesian product, but then if your probability distribution doesn't come from this kind of product type thing, would it?
Yes, yeah, that's also good. Yeah. But for the longest time, I was thinking of paths. But if you're interested in this, given that I'm out of time, so there's some results. There's a work due to Elster K that actually look at this. That's very interesting because it has something to do with inverse eigenvalue problems on essentially Jacobi matrices. But it's not conclusive actually whether Bob can win on all the paths. Okay, so I've sprinkled some questions, and I think I'm really out of time. And I thank you for your time.
Well, thank you very much for a very nice board talk. Any questions?
Or complaints?
It's a very nice board talk.
Thanks.
So, Tino, can I just ask naively about the topology of this last problem? So once I choose the edge weights, then for each vertex, I just have a single parameter. You know, I have something of Hausdorff dimension 1 wandering around inside the probability space. And so measure theoretically, it's hopeless unless I'm able to change these edge weights. But now what's the degrees of freedom with the edge weights? What's the dimension? I mean, you're sort of changing the dimension of the manifold by changing the edge weights, right?
So I guess, yeah, so I think when we were thinking about this with the students, so we were only thinking about essentially trees, because we know you need connectivity, and we are wondering like what is the smallest kind of well, trees would be the smallest connected thing, and cycles probably are redundant. So we'd like to then the dimensions sort of matched up almost, kind of, right? Right. So too many edges, I'm not sure. Too many edges might kill this problem actually. Claws are okay. Paths maybe, but maybe pick your favorite tree and then ask the same question. I'm not sure. You're asking about the dimensions not matching up or something, right, Bill?
I guess what I'm asking is, instead of fixing the weighted adjacency matrix and changing the time, what if I fix the time and ask what's the space of state vectors that are covered as I vary the adjacency matrix at that particular time? Right? That's where your degree of freedom comes from. Is there any description of that space?
So good point. So if you look at Kay's paper, I can give reference to this. So what Alistair did was he fixed time actually. He fixed time to be pi, and he rigged his essentially what he's trying to do is he's trying to rig his tridiagonal matrix with a carefully chosen eigenvalues and eigenvector actually, so that this happens. So he can cover any distribution, and it's a pretty simple sort of choice actually. He just needed this matrix to have eigenvalue 0 with a prescribed eigenvector, and every other eigenvector has to be odd. So this is special, and this is actually not too relevant. So he needs a matrix that has 0 eigenvalue, and the other eigenvalues are odd integers. And then he's going to find the weights on the path that is going to cover that distribution. It becomes like an inverse eigenvalue problem, actually.
So if Bob wins, is the set of times at which he wins dense?
I don't know. That's a good question. I don't know. You mean whether he wins infinitely often?
Yeah, it's something like that.
Yeah, I don't know. Good question.
Yeah, but there's a trade-off between the time and the weights. And so the natural thing to do is what Alice did and pick a time and see what you can do at that time.
Yeah.
Because you have in the transition matrix, you got a product T times A. And so you can move weights backwards and forwards from T to A.
So another variation is whether you can like optimize the weights so that you don't use all different weights. Maybe it's from a smaller collection, so the weights don't look too diverse. But yeah, it's not clear.
Tino, this might be a silly question, but do you know other graphs where Bob can win on some vertices but not others? Like, are those two versions of the game, are they actually provably distinct?
So yeah, on the claw, yes, on the claw, it's easy to prove that Bob can win from the conic vertex. This is pretty easy because this is resembling a K2. With a little bit more work, we can handle the non-conic starting point. So we have to start somewhere here. Then you have like a P3 type thing. But to answer your question, no, I don't know example of graphs where it's sensitive. So Mike, you're asking whether there's two conditions, right? Yeah.
Well, I was sort of wondering if could it be just something like a pathological limb of a tree, which as long as you have that, then Bob loses on those vertices.
Yeah.
I'm kind of remembering Schwenk's proof, but I don't know. It's a really nice game.
Yeah, that's a nice question actually that you ask. Yeah, that would be. So Harmony asks, what if he can only add weighted loops? Weighted loops.
I don't know if this is known, but for the PN, do they add loops as well, or they just change the weights?
You mean
on the edges?
For this
paper by K.
I think Alistair probably allows self loops, but I don't think he uses it, if I'm not mistaken. I might be wrong. I have to check. No, that's a good question. But Harmony, you're asking, are there graphs for which just adding self loops
it will help?
Will be enough for Bob to win?
Yeah.
I don't know. I don't know.